Hello and welcome to this crash course where you will learn about cryptography. Cryptography can be a bit challenging for beginners, but I have simplified it with animations in this course. Cryptography is an absolutely essential component of secure data communication in modern computing. It is a must-know for everyone, especially network and cybersecurity engineers. We will cover these topics: what cryptography is and why it is needed, basic cryptographic terms, symmetric encryption and asymmetric encryption. So let's start with what cryptography is and why it is needed. Cryptography, in simple terms, protects data. It allows devices to communicate securely over the internet. It protects data from cybercriminals, middlemen, or hackers. Let me first demonstrate data communication over the internet without cryptography. Then we will be able to understand why it is needed. Suppose device A and B want to communicate over the internet. A sends a hello message to B. Now, the data does not travel directly from the sender to receiver on the internet. Instead, it goes through various devices and networks to reach the destination. We don't know who can intercept the data as it travels to its destination. Now, what if a cybercriminal intercepts the communication? Then the hacker will be able to read all the details or data that the communicating devices exchange between them. Intercepting data is not that difficult. If you have basic hacking skills, you can intercept data easily. The problem becomes even more critical when users connect to important websites like banking portals, Gmail, or social media platforms. Interception of data communication with banks or other sensitive websites by hackers can have severe consequences and compromise your personal information. We have no control over who might intercept data because by design the internet is accessible to everyone. The real problem here is the communication of data in plain text. Devices are sending and receiving data in plain text, so whoever intercepts it can easily read the original data being exchanged. Therefore, we needed a secure method for safeguarding and exchanging data. This is where cryptography steps in to address the problem. Cryptography encrypts the data before it is sent to the receiver. After encrypting, the data becomes unreadable like this. The hello message gets scrambled into this unreadable encrypted text. Now, this encrypted message is then sent to the destination. Now, even if cybercriminals intercept the data, they will not be able to read the original data. All they will see is the encrypted data. The data is decrypted or converted back to its original form only at the destination. This is the magic of cryptography. Only the receiver can decrypt data back to its original form. So that's how cryptography protects data and ensures it is delivered securely to its destination. In this video, we will clarify some basic terminology used in cryptography, such as what is encryption, decryption, and the difference between encryption and cryptography. So let's start with encryption. Encryption is a process of converting data or information into an unreadable form or format. Let's say the sender wants to send a hello message to the receiver. Now, before sending the message to the destination, encryption scrambles or encrypts the message into unreadable random characters like this, so that only the authorized or intended receiver can read it. Data is encrypted in a way that only the intended receiver can read the original message. This encrypted data is then transmitted to its destination. Now, if hackers hack or intercept the data, they will not be able to read the original message. Attackers will still be able to access or view the data, but all they will see is the encrypted message, not the original data. Now, decryption is the opposite of encryption. Once data is encrypted, it is sent to the destination, and at the destination the encrypted data needs to be decrypted so the receiver can read the original message. Now, the process of converting encrypted data back to its original form is called decryption. Remember, only authorized users can decrypt the data. Data is always decrypted at the destination. Now let's discuss the difference between encryption and cryptography. Cryptography is a broad term that includes everything related to data security. Encryption is essentially a component or part of cryptography. Cryptography, on the other hand, covers everything related to data security, including encryption and decryption, along with all the necessary steps involved in the data security process. So cryptography is a comprehensive term that includes everything related to encryption and decryption. Both are integral parts of cryptography. When it comes to encryption, there are two primary types, symmetric and asymmetric. In this video, we will specifically focus on symmetric encryption and how it works. Now, symmetric encryption is also known as symmetric key encryption. It uses a single key to encrypt and decrypt data. The word symmetric means the same. Therefore, symmetric key encryption uses the same key to both encrypt and decrypt data. This key is also known as the secret key. The concept of key in symmetric encryption is very similar to a door key. We use the same key to both lock and unlock the door, right? Only the key that locks the door can unlock it. The same principle applies to symmetric key encryption. The same key is used for both encrypting and decrypting data, and no other key can perform these functions. The data is encrypted using complex encryption algorithms. An encryption algorithm is essentially a technique or a set of steps used for scrambling or encrypting data. There are many encryption algorithms used in symmetric encryption, such as AES, DES, Blowfish, etc. to encrypt data in real-world applications. Now, I will explain symmetric key encryption using the simplest and oldest encryption algorithm. This will help us easily understand the process and how an encryption algorithm and a key work together to encrypt and decrypt data. Encryption is not a new concept. It has been used for centuries to protect information even before computers and digital data existed. The first known data encryption method was used by Roman King Julius Caesar. The technique or encryption is also known as Caesar cipher. The Caesar cipher is one of the simplest and oldest encryption methods, named after Julius Caesar, who used it to protect his military messages, such as when to attack, retreat, etc. Caesar cipher serves as a foundation for understanding the concept of symmetric key-based encryption. Now let's understand symmetric key encryption using the Caesar cipher. Let's say that device A wants to send the message hello to device B securely. As I mentioned at the beginning, the message is encrypted using a secret key in symmetric encryption. Let's say the secret key is 2. Now, the encryption algorithm or Caesar cipher works by shifting letters forward by a fixed number of positions. In this case, we are using 2 as a shift value, so it will move each letter 2 positions forward. Caesar cipher is also known as Caesar shift or shift cipher. The algorithm specifies shifting or moving letters forward by the secret key value for encrypting data. In my case, the secret key is 2, so we will move each letter forward by 2 positions. So if you move H 2 positions forward, it becomes J, E becomes G, LL becomes NN, and O becomes Q. So this is the encrypted data or text. Hello has been encrypted into this. Now remember, this is very important. This encrypted text or message is known as the ciphertext in cryptography. Ciphertext is basically the encrypted message or data. Now, after encrypting the data, A sends the ciphertext to the destination. The receiver uses the same secret key, which is 2, to decrypt the data to its original form by reversing the process. The encryption algorithm involves shifting each letter 2 positions forward in the alphabet to encrypt data, right? Now, to decrypt the message, the algorithm reverses this process by shifting each letter 2 positions backward. For example, the J becomes H and the letter G becomes E. The letters NN becomes LL and Q becomes O. Now we have successfully restored or decrypted the ciphertext to its original form hello. This process is known as decryption. So that's how the algorithm and key work together. The algorithm specifies the shifting of letters by the shift value, while the shift value itself is the secret key. Now, if A wants to communicate with other device, it generates a unique secret key for each connection. Computers or devices in the real world don't use or rely on simple encryption methods like the Caesar cipher to encrypt data, because the Caesar cipher can be decrypted very easily. The Caesar cipher method is a valuable tool for explaining the concept of symmetric key-based encryption. The encryption algorithms utilized by computers involve highly complex mathematical equations. Encryption algorithms that computers use, such as AES and Blowfish, use sophisticated mathematical calculations to encrypt data. AES is the current industry standard and is highly secure. It is used for securing communication. Now let's address the very important question: how does the receiver know or obtain the secret key? As we discussed earlier, both the sender and receiver need the same secret key to encrypt and decrypt data, right? If the sender uses 2 as the secret key to encrypt data, then the receiver needs the same key to decrypt the data. This means we somehow need to share the secret key with the receiver so it can decrypt the data using the same key that encrypted it. However, sending the secret key directly to the receiver is not safe. Let's say if the sender sends the secret key directly along with the data to the receiver, then hackers can intercept both the secret key and the ciphertext. Consequently, they can easily decrypt the message using the secret key. That's why the key is not sent directly from sender to receiver. Instead, the key is exchanged or established securely using the Diffie-Hellman protocol. The Diffie-Hellman protocol uses complex mathematical equations that allow both the sender and receiver to independently establish the same secret key without directly sharing it. So Diffie-Hellman essentially helps both the sender and receiver establish the same secret key without directly exchanging it. Remember, the secret key is always established before both the sender and receiver start exchanging actual data. After establishing the key, both devices then begin exchanging data securely. It is a proven method for key exchange and is considered extremely difficult for a third party to intercept or predict the key. In this video, we will discuss the second type of encryption, which is asymmetric encryption. Before we dive into asymmetric encryption details, let's explore why asymmetric encryption was developed. Asymmetric encryption was developed to address the limitations of symmetric encryption. As we discussed in the previous video, symmetric encryption requires the sender and receiver to share a secret key before they can start exchanging data. While the key exchange is typically secure, however, there is no absolute guarantee of security every time. A slight possibility of compromise always exists. Both symmetric and asymmetric encryption have their own unique applications. Now, asymmetric encryption solves the key sharing problem of symmetric encryption. Asymmetric key encryption is also known as public encryption because it uses two separate keys to encrypt and decrypt data, the public key and the private key. The public key is typically used to encrypt the data and the private key is used to decrypt it. The public key, as the name suggests, is either publicly available or shared with authorized recipients or receivers. The corresponding private key is kept private and is not shared with anyone. Now let's understand the essential fundamental terms of asymmetric encryption before diving into how it works. Let's say A wants to send hello to device B. Now, before exchanging the data, both devices will generate two keys each, the public key and the private key. The public and private keys of each device work together because they are always mathematically related or linked together. Remember this point, it is very important in asymmetric encryption. Suppose if device A encrypts its data with its public key, then that data can only be decrypted using its private key. No other key can decrypt it. Similarly, if A encrypts data using its private key, then the data can only be decrypted using its public key. As I mentioned earlier, both keys are mathematically linked together. So if you encrypt data with one key, then only its corresponding key can decrypt that data. The same applies to B and all other devices that use asymmetric encryption. If B encrypts data using its public key, then only its own private key can decrypt the data and vice versa. In the real world, the public key is always used to encrypt data and the private key is used to decrypt it. Therefore, the public key is shared with other devices. Now let's see how the entire communication is securely carried out using asymmetric encryption. Suppose A wants to send the hello message securely to B using asymmetric encryption. The first step in asymmetric encryption is that both the sender and receiver generate two keys each, a public key and a private key. Now, after generating keys, both A and B will exchange their public keys. A will send its public key to B and B will send its public key to A. After receiving the public key of B, A will use public key of B to encrypt its data. The hello message will be converted into ciphertext after encryption. Now, the encrypted data or ciphertext is sent to B. Now, how does B decrypt the data? B has two keys, its own private key and the public key of A, right? Remember, the data B received was encrypted using its public key, which it sent to A. Now, only the private key of B can decrypt the data because it's the only key mathematically linked to it. B already has that private key. It shared its public key and kept the private key. So obviously B decrypts the data using its private key because the data that A sent was encrypted using its public key. So the private key of B will decrypt the data back to its original form, hello. The public key can't because it is not mathematically linked to the key that encrypted the data. So basically B says to A, take my public key, then encrypt the data that you want to send to me with it and then send it to me so I can decrypt it using my private key. Similarly, if device B wants to send data to device A, it will use the public key of device A to encrypt the data. Upon receiving the data, device A will use its own private key to decrypt it. So to summarize, in asymmetric encryption, both the sender and receiver exchange their public keys before exchanging data. So the sender can encrypt the data using the public key and then corresponding private key is used for decryption. That's why asymmetric encryption is considered more secure compared to symmetric encryption because you never need to share the private key that decrypts the data. The algorithm that powers asymmetric encryption is RSA. RSA encryption is an asymmetric encryption algorithm named after its three inventors, Rivest, Shamir, and Edelman. Asymmetric encryption uses RSA to securely exchange data over the internet.